Hello everyone, I'm Mike Simmons, the founder and president of Astronomers Without Borders, and this is the first of a short series of special Hangouts this week for Sunday, or as Teresa, our solar coordinator, puts these together, puts it a week of Sundays. So we had in our Sunday yesterday, and with solar observations and so on around the world. But now we have a special program with Dr. Matt Penn, who is a telescope scientist at Mcmath Pier solar facility, which is one of the largest telescopes in the world, tied for the largest, and two additional telescopes. So it's really three of the world's largest solar telescopes here. So welcome, Matt.
Hello, Mike. Nice to talk to you.
And so Matt is joining us from the National Solar Observatory headquarters in Tucson, right below Kitt Peak Observatory. I wasn't able to make it up the mountain to show us around, but we have some pictures of that as well. And Matt, I understand that your duties cover quite a bit. I mean, in addition to being an astrophysicist and solar astronomer, you take care of the facility itself in many ways.
Right, yeah. Some of the pictures show the facility and some of my duties. You know, telescope scientist sounds like a really lofty position, but when it comes down to it, you end up doing things like washing windows and cleaning other parts of the facility as needed. Telescopes are, you know, sometimes fickle instruments, and when things go wrong, you just have to figure out a way to make them go right and fix whatever is happening.
Okay, here I am. I don't know what that looked like there, but all of a sudden Google kicked me out. And Liam,
but I just unmuted myself. Anyway, just to jump in, just in case you didn't manage to get back. So
yeah, well,
anyway, I'll fade back into the background, and you two can carry on.
Yes, well, I'll try, because I was about to share my screen to be able to show some pictures from Kitt Peak to show Matt at his duties, and that's when something crashed. So I'm going to try again.
Sounds typical, Mike. We can be at the telescope on a sunny day and things crash, and
I
figure it out.
What happens? You don't usually have an audience for it like we do here. So I'm going to try something a little bit different. Please work this time. Okay. I'm still here, so this is probably working, and I've made this, it's going to appear in a slightly different way on here. I was going to share just the window, and I'll try that again. Maybe we're going to have to loop through these. This is a PDF of slides, so maybe I can boost that up to watch everybody watch me do this live on screen. So here is the Mcmath Pier Solar Telescope. Now, Matt, that's part of the telescope. But
right.
A large part, maybe the majority, I don't remember, is underground here.
Yes, the majority is below ground. The Mcmath was designed in the 60s when film was the detector of choice. And so one of the key design criteria is to have a big solar image. The Mcmath has 3 telescopes in it, and they all have very long focal length mirrors, so that the images they project in the observing room, which is at ground level there, are large. In order to escape the seeing that we have, the turbulence that we have on the ground, the tower rises 100 feet above the surface of the ground. And then we have flat mirrors on the roof which track the sun across the sky during the day. But then at the bottom of the tunnel, some 140 meters away from those flat mirrors, we have the focusing mirrors. We call them the primary mirrors of the telescope. And because they're so long focal length mirrors, we have to have them buried under the ground in a tunnel that extends twice as far below ground. So off to the right of that image, you can see the telescope reaching down to the ground, and it extends about twice that far below ground.
Mm-hmm. And then we have a couple of pictures here. That's not the right way to show them, but it'll get the point across. Here are
Right.
you at your duties. Now, this is for those people who see astronomy as a very romantic science that maybe this
Right.
changed their mind. You, I don't think you're always doing this kind of stuff up there.
Well, sometimes you have to wash the windows, and it can be exciting on top of the tower there. But
Yeah,
washing the primary mirror is something that we have to do regularly. It's out in the open, and the birds kind of like it.
yeah.
And then occasionally, the bathroom has problems, and if no one else is around, the telescope scientist has to do it. So my point about the bathroom janitorial picture is that because we have some budget cuts, we can only afford one glove for the telescope scientist. And things are getting tough now.
That is tough. Okay. That's terrible. Well, and we do know that, and we'll talk about this a little bit here too. That the Mcmath Pierce, I mean, has had a 60-year history now, almost, of incredible solar research.
Sorry.
Yeah, and so it's about to be supplanted by another telescope we're going to take a look at. But let's take a look at the sun itself, because the whole point of this hangout today, and I should mention that, is that there is an eclipse coming up in 2017, which, and I believe you've been to solar eclipses yourself, Matt, is that right?
Yes, yes, I've been
Yeah.
involved in two in the past, and would like to increase that number and do some science.
Yes, and I've been to 7 just for the experience. It's worth, I can't chase around the world to all of them, but it's absolutely unbelievable. And this one coming up in 2017 is going to cross from the northwest to the southeast USA. There hasn't been an eclipse that would cross the US like this in a very long time. And the
Right,
last
it's
one
been
in the continental United States was in 1979. That was my first.
exactly.
So, but the thing is, and this is something not all of us who chase these eclipses when we can know, is that there is science to do still with eclipses that cannot be done from the ground, cannot be done from space. And you want to recruit amateur astronomers and normal people across the country to take part in this scientific, unique, one of a kind experiment to capture some data from this eclipse.
Exactly. We live in a really unique time. Some of the uniqueness is not so good with budget cuts, but citizen science is really blossoming now these days. And so the opportunity to look at the eclipse that crosses the whole continent of the United States, using citizen scientists and getting them involved in a type of research project that's never been done before, provides us with an exciting and a unique chance in 2017.
Yeah, and this was something I didn't even realize was in the cards. I know there's a little bit of science done, but this is really important. Just to make sure, it gives some people a little bit of background. We won't dwell on this. I want to show your cutaway of the sun here. Please let me not go away when I do this. Ah, okay, it's working. So here we have a great cutaway of the sun that you provided. Now, what we see when we look up at the sun with safe solar filters is
Yes,
the photosphere there with the sunspots. And there are specialized telescopes that many amateurs have now that can show the chromosphere and the prominences.
exactly.
And all this kind, I don't think we need to go down to the core and work our way out there. So let's stick with this because we see this. But the part that you do not see under any circumstances, except during an eclipse, is the corona here. Little wispy stuff sticking out of there like hair.
Exactly. The corona is a mysterious place in the sun. It's at some crazy temperature. The surface of the sun is about 6,000 Kelvin, but as we move up into the atmosphere of the sun, we encounter the corona, which is actually at 2 million Kelvin and sometimes hotter. So even the basic physical processes that are going on in the corona still mystify solar physicists. What compounds the problem is that it's very difficult to observe. We can observe it from space using some spacecraft that look at the extreme ultraviolet radiation, or we can block out the disk of the sun from space and use a coronagraph. But really, the best coronagraph that we know about uses the moon as the occulting disk, and that's what happens during a total solar eclipse.
So, which is just amazing this day and age. I think that we don't have the technology to be able to do it quite perfectly. But there are other impacts of the solar corona itself. It's something that's coming out from the solar surface in a way that we don't really understand. But there's a solar wind as well, and that's been in the news since Voyager has reached the heliopause, which caused a lot of confusion. People saying it's in the solar system, it's out of the solar system. There are different ways of measuring it, but we have something here to show that maybe you can explain about that as well.
Yeah, so the sun really extends throughout the entire solar system. The atmosphere of the sun really encompasses the planets in a bubble called the heliosphere, and through that outer atmosphere of the sun blows the solar wind. It's a stream of highly energetic charged particles that travel outward from the sun. When those particles encounter the local interstellar medium, that is the gas that's in the stars, near the sun, and the pressures balance, that's where this shock wave forms, where this transition between sort of our solar environment and the rest of the galaxy occurs. And yeah, there was some confusion about when Voyager 2 or Voyager 1 had crossed that transition, but we think that now it's firmly past that and into the interstellar space region.
Mm-hmm. So this is the interstellar space, sort of the wind from other stars pushing back against the solar wind.
Right, and of course we can't see that directly from our view inside the bubble, but what we can do is use Hubble to look at other stars, and in the lower right of that slide you can see a picture of a star in Orion, which demonstrates or shows a structure that we think really exists around the sun as well, a little bow shock and a solar wind coming out of that star, a stellar wind. We think that our solar system looks like this. And this really sort of encapsulates one of the main ideas that I think people today need to keep in the back of their head, is that we really live inside the outer atmosphere of the sun. We really don't talk about winds on the moon or Mercury, places without an atmosphere. A wind really, you need an atmosphere to have a wind. And so the fact that the solar wind is blowing past the Earth and the moon really lets you feel, or gives you an intuitive understanding that we live inside the atmosphere of the sun. So when there are storms now in the atmosphere of the sun, solar flares or CMEs, it's not surprising that they have a big impact on the Earth.
Mm-hmm. Well, and they do. I mean, solar flares, of course, they cause the aurora. We get to see lots of nice, pretty pictures, but they can cause damage or difficulties here on Earth as well. So this is not just a matter of pure science, trying to understand what the very outer atmosphere of stars is like, but it's something we really do need to know about.
Right. It has a direct impact, and the more reliant we become on space assets for our communication, for our banking, or for other things, the more of an impact the sun and the space weather that it emanates from it will have on our lives. So, I've got this story that I am really fond of, is that when I was many years ago as a younger astronomer going up to Kitt Peak one day, there's not much between Tucson and Kitt Peak, maybe one or two gas stations. So I was driving to the mountain at 5 o'clock in the morning one day, and I tried to buy gas with a pay at the pump with my credit card, and it wouldn't take my credit card. So I tried it over and over, no luck. So I was careful and drove up to the mountaintop very economically, and figured that by the time I got back to the gas station, around dinner time, there'd be people there, and I could buy gas again. But when I got to the telescope, I understood that there was a CME, a solar storm, that had erupted earlier that day, and it knocked out, or well, it coincided with a spacecraft anomaly in the Galaxy 4 satellite. And this satellite was responsible for taking the information from pay-at-the-pump sites and making sure that with the banks that the user for the credit card had the right funds to pay for gas. So that morning, it wasn't just me, it was tens of thousands of people couldn't buy gas because of a solar storm.
And you have the price tag on that slide we're showing there of the gas station, a very lonely road when you're low on gas, and the Galaxy 4 satellite, $225 million, which would probably be This is a little while ago, you said, so
Oh yeah,
this
this
could
is
be 500.
1997, right? So you have to inflate that number, and companies are very aware, and these are the main customers for our space weather forecasts now that come
Hmm.
from data from the NSO and through NOAA.
Hmm.
They want to know what the likelihood of their satellites having anomalies are, and how to prevent that.
Now, you mentioned magnetic fields, and all of this is leading up to a little background on what you actually see during the total solar eclipse. One of the amazing parts of it, though not the whole thing, it is just an amazing natural phenomenon, but what the amateur astronomers will look at across the continent and help record to do this science. So I want to show one more here that talks about the magnetic field.
Right.
And
So,
this looks like kind of a mess. What in the heck? Okay.
well, the changes in the magnetic field and the corona are the key things, the triggers for a lot of the solar flares and the coronal mass ejections that cause space weather storms. But the problem is that we can't directly measure this. We have problems measuring the plasma magnetic fields, even though we can see that the gas is controlled by magnetic fields and it has loop structures, things that look like iron filings that
Hmm.
are arranged by a bar magnet. Understanding the value of the magnetic field in the corona and then how it changes with time is something that we're struggling with. The best that we can do currently is to estimate it with a method called the extrapolation method. So we can measure the magnetic field at the photosphere fairly well. We've done that for 100 years or so now. And then by making an assumption about what the magnetic field is further up in the corona, we can basically fill in the remaining space, extrapolate the magnetic field, and understand what it is in the corona.
Hmm.
Now, the models are getting pretty good, but the details of, if you zoom in on parts of this image, you'll see that some of those magnetic field lines in the model are just wrong. And then understanding how they change with time is something that is really beyond the scope of the models. So
Hmm.
what we'd really like to do is to have real-time, high cadence measurements of the magnetic fields in the corona to try to understand the physics, not only of flares and CMEs, but also of the heating of the corona.
Yeah, yeah. So, this is kind of amazing to me because, I use an old solar telescope at Mount Wilson for student programs, and it's well over 100 years old, and things have been worked out pretty well since then, but the corona remains still a mystery despite more than a century of really good astrophysics work that's been done on the sun.
Yeah, there are challenges. It's a million times fainter than the disk of the sun, and it's what we call a background limited problem in astrophysics. The background signal from the sky or from your telescope makes important contributions, and even though you subtract the background perfectly, you still have noise from your background that interferes with the measurement of the corona.
Hmm.
So it's providing a very tough challenge. Now, we've made some progress in recent years, actually at the past two eclipses that I was happy to participate in, where we've found out that there are spectral lines from infrared emissions coming from the corona. And we've known for 20 or 30 years now that infrared lines allow us to make more magnetically sensitive measurements, and we use them now in the photosphere. But what we'd like to do is to use those infrared emissions from the corona to measure the magnetic fields there.
Hmm. And that leads us to this thing, which is something that I think most even amateur astronomers don't know about. There aren't that many solar telescopes around. Uh, but here we have one that is being built in Hawaii, on Maui, and it has a mere 4 meters across, a 4 meter solar telescope. So anybody that's used even a magnifying glass to focus the light of the sun understands this is a lot of heat.
Exactly. It's a four meter magnifying glass, and it's a very fast focal length. Unlike the Mcmath Pierce, it focuses the sunlight to a prime focus only a few meters up inside the building there. So there's a lot of heat energy, and it's a really technically challenging telescope to build. It's called the Daniel K. Inouye Solar Telescope, and we're in the process of constructing it now on Maui, on the volcano there on Haleakala, in the Science Center property there. So there are huge challenges with the telescope, but the engineering team that we have here is world class. The designs and the performance tests so far say that every optical element in the train will stay within 1 degree centigrade of ambient temperature.
That's incredible. Well, good luck with that. And I'm going to flip through a few pictures of this under construction here, but this is really enormous.
It's an exciting instrument, and we're really happy to have the chance to build it. We've got partners from all across the country and some partners from Europe as well who are contributing instruments. And so in addition to looking at the solar corona and the magnetic fields there, we're going to look at very fine details on the solar photosphere that no one's seen before, and study sunspots and other things in detail that no one's ever dreamed of. So we hope to do some really breakthrough science to understand our nearest star with the DKIST telescope and its instruments. We're hoping for first light in 2019, and stay tuned is what I can say.
Yeah. Well, this has been long delayed when it was Advanced Technology Solar Telescope, and it's been a long time coming, but it'll be great when we have it. So, in the meantime, let's go back to solar eclipses, and I'm going to be scrolling through these in a very unprofessional way here. But so, the National Solar Observatory in the U.S. has been observing eclipses for many decades, and this looks like an example of one many decades ago.
Oh yeah, this is from 1965, an eclipse in the South Pacific, and some of my colleagues are there boarding their flight to Los Angeles or Honolulu, and then another picture shows them in the island in the South Pacific after they took the yacht there to get to the island. So, I mean, Eclipse Expeditions were very exciting science when we could look at the corona without having the background of the Earth's sky in the way, or any instrument scattered light in the way.
Right.
So this team of 30 people, as well as some people in aircraft above the islands, flying in the path of totality, took some really breakthrough scientific data and studied the decay of the intensity as you move further out into the corona, and the emission lines of particular colors in the visible spectrum, and produced really wonderful science from their experiments. There's 5 or 6 or maybe even a dozen scientific papers that use data from these experiments. Times have changed now, and so I don't have a team of 30 engineers and technicians, and it'd be a little hard to justify a cruise to the South Pacific. So we're going to approach 2017 in a very different way.
Well, and let's get back to the eclipse here and talk about that. This is the CATE experiment. This is what you want to recruit people for. Right.
So it's called the Citizen Continental America Telescopic Eclipse Experiment, and so we're hoping to get people involved and do something revolutionary, which is to actually track the shadow of the moon as it moves across the continent. If you're in any one location, and we call it Citizen CATE Experiment because there are some references to a movie. So let's just say that you were in Rosebud, Missouri, which will experience totality. If you're sitting there in the park in Rosebud, you'll see totality and the corona around the sun for only 2.5 minutes. But if you look at the time the shadow of the moon enters the Oregon state and figure out how long it takes the shadow of the moon to leave South Carolina on the exit, 90 minutes of time have elapsed. So in theory, if you had telescopes along the entire path and then took data from each site, combined it after the eclipse, you would be able to observe the corona for 90 minutes continuously. And that's the ultimate aim for the project.
Which definitely, that's far beyond anything that's been done. I have seen some results from certainly images in different locations and people trying to line up individuals along the path to take pictures, but to this extent to be able to get a video for this entire time. And we can see here going all the way from Oregon down to South Carolina. Hopefully people all along the way. So that's, how many people do you need to get involved in this?
Well, in theory, if we had roads everywhere and no mountain ranges, for instance, we might be able to do with 45. But by taking a first cut at looking to put people in places along the road or in city parks. We can do it with 60. Now, of course, we have to fold in the weather because it may or may not be perfectly sunny across the entire path on eclipse day. And so we're thinking that perhaps we'll get between 60 and 100 sites along this eclipse path.
So, are you citizen scientists to do this? They have to be right on the center line, or are you using people that are a little bit off of that? Because we could see from that last plot, the map that shows the path. I mean, this is a very narrow path, but moving a little bit away from the middle can help sometimes with a little bit of weather too.
Exactly, and we have people that are scattered north and south of that line a little bit. We'd like to have them as close to the central line as possible to maximize the overlap between sites. But certainly, I think in August you don't want to be on top of a mountain because you'll have local thunderstorms building up. And so having somebody slightly off of the mountain and off of the center line then would be advantageous for collecting data. Some of my colleagues at Western Kentucky University are going to look at this in more detail and combine the path of the eclipse along with the latest meteorological data to see exactly where you might have an optimal location for sites to maximize your coverage of the eclipse.
Yeah, and so I want to share one other here. You're going to have to tell me what's going on with that, and I'm sorry, let's see here, there we go. Because I had a question for you. We were talking earlier, and I said, well, we can see the corona from space. So why do we need to do this? But it turns out we can see almost all of the corona from space.
Right, and this is a great slide to show where a solar eclipse actually fits into the puzzle. We've got data from 2 space missions, one that looks at extreme ultraviolet radiation, and that shows us the disk of the sun, which is in the center of this figure, and then a little bit around above the limb of the sun, maybe out to 1.1 or 1.2 solar radii. We have coronagraphs in space which block out the disk of the sun and allow us to see closer and the corona beyond that. And here we have data from the LASCO C2 coronagraph, and that gets down to about 2.5 or 2.2 solar radii. But in the intervening space, we're really missing good data. It's difficult to observe that with a space coronagraph because of the scattered light that's involved and the accuracy of the pointing that's required. It's difficult to observe that with the EUV radiation because the intensity of that radiation that we see on the disk of the sun drops off quickly with distance. So the solar eclipse really opens up a window that allows us to see that part of the corona in detail. And we know that there are some interesting physics that go on there. We know that the solar wind accelerates from about 1 kilometer per second at the bottom of that region near the surface of the sun up to 100 kilometers per second at about 2 solar radii. And then we know that the magnetic field of the corona goes from a complicated structure with loops to a very radial structure that dominates the outer part of the corona and the solar wind. So how the corona makes that transition is still not really well understood. And the solar eclipse, opens a window for us to study those things.
Well, and we have a video also taken from satellites, and we'll get Liam to play that for us. And note that with a total eclipse, you see everything from the chromosphere, like what you see in a H-alpha telescope that's very popular now, all the way out through the inner corona, the outer corona. You see everything all at once. But in the video we see here, there is some area that is not covered at all. And yeah,
right,
maybe
exactly.
explain the parts of this here.
Yeah, so again, on the disk of the sun, you can see an extreme ultraviolet light image of the sun. And then we encounter that zone that space missions don't sample very well, about from 1 to about 2 solar radii. Then we encounter then you can see data from the LASCO C2 and the LASCO C3 coronagraphs showing the 2 layers of the corona. Here you can see some CME events, coronal mass ejections that occurred in 2003 that were highly disruptive when they encountered the Earth. But yeah, the details of how these coronal mass ejections are launched from the sun and then what the acceleration mechanism is hidden in that little black ring, and that's what we're studying during solar eclipses.
So along with the excitement of it all, and you and I both know the excitement. Nobody who hasn't seen a total solar eclipse really understands what the big deal is. But it's not just the sun. My own little story was I was working at a big public observatory here in Los Angeles in 1979 as the eclipse approached, running the telescope, answering questions. And people asked, well, what will this be like? And I told them all about what the sun would look like, and realized I was just misinforming everybody completely because I had no idea. It wasn't my fault. There was no way to know when the shadow overtakes you, when the stars come out, but it's like sunset all around. And the sun itself, I looked up at it and said, is that the sun? It's not like the pictures. It was just so far beyond that. So I really didn't know what to make of it. So I hope people will get out there.
Oh yeah.
Yeah.
And since you've seen several eclipses, you know that it doesn't matter what culture you're in or what country you're in, people react the same way. There's something that's just wrong when the sun goes away. It's something that we depend on, and when it's not there, you just feel it in your stomach.
Yeah, there's something wrong, and you can understand how people, not knowing what it is, would be extremely frightened, because something primal in me is really frightened when this happens. I mean, it's an amazing thing. So let's see what we're going to have a chance for the amateur astronomers to do. And I've got your picture here of the equipment and what one can do with that.
Right. So we've got a prototype instrument here that we purchased at the NSO, and it's a modest telescope. It's an 80 millimeter refractor, and we have a digital imager on it, a CMOS camera in this case, 2K by 2K. And so the idea is to take images of the corona as rapidly as possible in order to maximize our duty cycle. That is, we want to collect all of the photons that fall on the telescope, or as many as we can. So we ran through some tests here in Tucson, and so you can see an image of the sun that's been, we've removed the limb darkening in this case, and so you can see sunspots and plage just using white light. But then the telescope itself, the solar eclipse, as I said, lasts 2.5 minutes, and getting good data from the eclipse is the priority of the experiment. But then what happens after the eclipse? People have a solar telescope, and what can they do with it? Well, we've taken some test observations at night, and here you see my modest effort at trying to capture the Orion Nebula from my back porch there with the telescope. You can see that the telescope performs reasonably well for nighttime uses as well. So it's a multifunctional instrument. Of course, the solar image was taken with an ND filter on, a neutral density filter, a protective solar filter. And if you take the filter off, then you can look at nighttime images, objects as well.
Mm-hmm. So for those of us who are into this kind of stuff, tell us the details of the equipment shown in that picture.
Well, I won't be able to give you any company names yet, of course, but we've got an 80 millimeter refractor that's 560 millimeter focal length. It's got a nice focal plane, flat focal plane, so we can get about a degree square field of view. And then we've got a 2K by 2K CMOS camera that's running really rapidly. We can get 45 frames per second off of this, with exposure times from about half a millisecond up to about half a second, 500 milliseconds or so. It's mounted on a very simple but sturdy German equatorial tripod mount, and we have just one right ascension drive on it. During 2.5 minutes, we're not going to need any declination drive. So we're just tracking the sun as it moves across the sky in right ascension. And then we've got a simple laptop. Right now, we're just running the free demo software that came with the camera, but we're hoping to develop a real package that allows users, when the eclipse happens, to take the filter off of the front of the telescope and push the go button, and then they can just enjoy the eclipse experiment themselves without having to type anything during the eclipse. We'll have a timer, and when the eclipse time is over, it'll beep, and they'll put the filter back on the telescope, and that'll be it.
Yeah.
We'll need to do some.
I'm sorry. Go ahead.
We'll need to do some calibration observations as well, as everyone knows who takes digital images, flat field and dark corrections, and then also drift data to understand the pointing. Everybody's going to put the camera in slightly differently, so we want to understand how they align the camera
Okay, now tell me, what kind of people are needed for this? Do they have to understand what flat fields are and what all of this means? Some
Well,
experience at it?
well, ideally, we'd like to have those kind of people involved as well. And some of the images taken by citizen scientists, citizen astronomers, are just mind-boggling to me. I mean, people are doing amazing things with H-alpha and even white light on the sun,
Right.
things that we have a hard time doing at the National Solar Observatory. But what we've done is we've actually used a guinea pig, a test particle. Citizen volunteer Fred Isbiner, who had actually never taken an image through a telescope before. Turns out that he was going on a trip, on a vacation, to see the March eclipse in the Faroe Islands just last month.
Mhm.
And he had gotten in contact with us in a workshop that we ran in Columbia, Missouri last summer, and expressed interest. And so the timing was a little hectic, but we were able to test out the prototype, pack it up, and send it to his hotel in the Faroe Islands, where he actually took some test data. So we've got a slide there. If you can bring that up to
Oh,
the
let's
very
see
next slide.
that. Let's see. Very next. Oh, okay. And that's
And Fred had only 2 days of training on the equipment. We're hoping to do better than that for the 2017 eclipse. Um, and also, Fred was using the prototype software, the demo software, and we're hoping to do a much better job for the 2017 eclipse with that. But in the upper left, there's a picture of Fred just on one clear day getting test data in Illinois.
hmm
And then on the upper right, he's setting up the tripod in somewhat less than optimal conditions in the Faroe Islands. It was raining. Um, but then, lo and behold, in the lower right, we see that clouds parted during the last parts of the partial phase. And Fred was able to get some of the drift data that we needed, as well as some of the dark black body or dark current tests. And then it stayed clear for about 30 or 40 seconds through totality. So on the lower left, we have a picture that's just a really rough analysis by me so far of the total solar of the corona that Fred captured with the prototype instrument. So here we can see some prominences as the very bright dots along the limb, and then we can see some of the lower parts of the corona, the loops that we see there. Now, Fred, we had this plan that if the conditions were right, he would go through 4 different types of exposure levels and expose out to see the outer, fainter parts of the corona. The clouds prevented that, and so all we were able to do was inner corona measurements. But from somebody who had never taken a digital picture through a telescope before to going halfway around the world and doing it in a 30-second window of time defined by the eclipse, I think he performed extremely well. And
With
we're really proud of what he's done.
yeah, very little preparation and training too, which will not be the case in 2017. Which may sound like a long way off for people, but it's not so much for preparation for this, as well as travel plans and everything else. I mean, anybody who can get into the eclipse path should do so. There's enough incentive there. It's a total solar eclipse. But in addition, this package is going to be provided for them to take part in the actual. I mean, when this resulting video comes out, should be absolutely astonishing, and to be a part of that would be great.
Right.
And I'd like to do it, and I can tell you that I've been to 7 total solar eclipses. I don't take pictures because I don't want to miss the experience. I sometimes take handheld pictures just showing the horizon. Sometimes it works, sometimes it doesn't. But this is just a great opportunity to be a part of this.
Right. We're hoping to have this data just freely available as well. I mean, everybody who takes part in the eclipse will be able to download the movie and use it for their talks or to show their family. Scientists from around the world will have access to this data. It'll be freely available, and we're hoping to have make this a very public experiment. We've got 4 hours of time from when the moon's shadow leaves South Carolina until the evening news that night. And in the summer of 17 and this summer, we'll be developing algorithms to take some of the images that we collect and assemble them into a first cut movie, so that hopefully on the evening news you'll be able to see your work, your participation in the experiment shown as this long movie. But these people who really, everyone's going to have to take Monday off from work and travel. You can't really reimburse their travel expenses as part of this. So what other incentive can we provide to them? What we're doing now is working really hard to find corporate and private money for the telescopes themselves. And the idea is, at least something that I'm really dedicated to, is that when the eclipse is over, that the volunteers from these sites will take the equipment home with them. These are people who are motivated to do science, as shown by the eclipse. We don't want these telescopes and the cameras sitting in a box someplace in a warehouse. We'd like to have them in the hands of people who will use them. And the hope is that we'll have a whole menu of different citizen science projects that they can do with the eclipse. Looking at sunspots on the sun and keeping track of those, looking at variable stars in the nighttime sky, making observations of comets. There's a project that does that now. We'd like to provide them with a whole menu of options for them to use the telescope after the eclipse as well, and try to reinvigorate citizen science in astronomy in our country that way.
Well, I have to say that if the 80-millimeter telescope is the incentive that gets them into the eclipse path, they don't understand the eclipse, because that's motivation enough. But until you see your first one, you don't really understand that. But I think that's great, because this engages people and keeps them engaged as well. But I have to ask too, and we have a question from Claude in California, somebody you and I both know actually, and Claude asks about after 2017, will CATE continue? Because we have an eclipse in 2016 in Indonesia. The chances of clear skies may not be as good. They're few and far between. Faroe Islands, Svalbard, Sweden, up in the Arctic Circle, this did not have the best weather prospects, but there were people who got there. Doing this whole thing across a continent and trying to get good weather through it, there are rare opportunities for that. 2017 is a great eclipse and maybe viewed by more people than anything in history. But there are going to be some in the future. Is this sort of thing going to be done later on as well?
Right. Well, there are two that we're looking at now, and only one of them is really, provides the same opportunity that the 17 eclipse does. There's one in 2019, which is exciting because it'll cross some large telescopes in Chile. It'll be late in the day near sunset for those telescopes, but there's a lot of scientific opportunity there. But then in 2024, there's an eclipse that crosses Mexico, the United States, and Canada on a south to north trajectory. And that has a lot of advantages as well. It's a much longer duration event. The eclipse is something like 4 minutes at every location. And then if we do have an army of volunteers who have heard about the 2017 CATE experiment and they're excited about the 2024 eclipse, we can do some exceptional science then. I'm hoping that detector technology, camera technology will improve by 2024, so the exact instrument may be different. But the concept, I think, is going to be relevant for 2024 as well. It'll be interesting, for your group as well, because it'll cross different borders, Mexico, United States, and Canada. And so organizing the international aspects of that experiment is something that I'll talk to you about.
Well, I was going to mention afterwards, but I'll mention it now. We're both going to be at NEAF the end of this week, and there are things that could be done with this. That could provide. There will certainly be webcasts around the world and so on. So I'm looking forward to talking with you if we either one of us or both of us have enough time to talk during a busy time like that. So we should talk about it, because there are tremendous opportunities these days, and by 2024 they'll be even greater. The optics might be exactly the same. I mean, the same telescope. I've used telescopes that are over 100 years old, and they still work great for the basics like this. The optics are just as good as ever, but the camera might be different, and our ability to bring it to people live and to gather it and to process it. All those things should be greatly improved as well.
Exactly. The lessons that we'll learn in 2017 will be really applicable to 2024, and people in Carbondale, Illinois are extremely excited about 2024. If you look at a map of the path of the 2017 eclipse and the 2024 eclipse, it crosses exactly in Carbondale, Illinois. So they'll just go out into their backyards 7 years later and see another wonderful eclipse.
That's now that you've let the cat out of the bag there, Carbondale will probably have 2 million people visiting in 2017. Many of whom will come back. Maybe they'll have they'll build huge hotels by 2024 for all the returnees with a big welcome back signs. But they
Yeah.
have quite an opportunity there as well. I have met one person who saw an eclipse twice in his lifetime without ever leaving home, same home. He was a poor farmer in central Iran, where I went for the 1999 eclipse, and the one he had seen earlier was, I think, in the 50s. So it's something like 40 years apart, but he must have been, in his 70s. So it does happen, but there are very few, and very few people have the opportunity to see a total eclipse. And everyone should take that opportunity if they have a chance. But fewer still are the opportunities to be part of a project like this. That is something more. This, in a way, it's even, to me, it's even better than the citizen science projects where you have thousands and thousands of people going through all the data and finding things. That's very, very important. But these are huge aggregate projects on really big, big data sets. Here, the people collect the data and that's it. So if you're talking about, 60 people or something like that, or maybe more, that's it. That's all the data there will be and all the participants there will ever be in this project.
Exactly. It's a very different approach to citizen science, and it's a new thing. It's kind of at a higher level than many of the citizen science projects that exist. But instead of training people to just go through a data set and use their innate abilities to pull out things that look different, or to take pictures of the flowers that are blooming in their yard with their cell phones, we're actually hoping to train people to use a telescope, a cutting-edge camera system, and a nice software package. I think there's a lot of excitement when I talk to other people about this, because there's now a group of 60 or 100 people in the United States after the eclipse that are trained on astrophotography, and that are have already volunteered for one project and are probably looking around for more projects. So we're really hoping that that at this level we'll be able to get people excited and motivated, and they'll continue to look at other science and make contributions after the eclipse.
Well, I want to go back, both in time and in the slide set here, to this picture that shows the expedition of 30 people setting sail to a South Seas island, or North Seas, I don't remember which it was, what the location was, and clearly going native. The ties are long gone by the time they're doing this. And this is typical because I've seen eclipse expedition photos in the Mount Wilson archives going back to the 20s, I think, and even earlier, and other eclipse expeditions, Venus transit expeditions going back to the 19th century or the 18th century actually. But that was a group of people who all went to the same place to do different things and make sure they got the observations from there. Now, the difference here, this is not even so much citizen science to me in a way, because these are the people going on this expedition, but instead of being at different telescopes in the same location, they're spread out farther, just on a bigger line. So these are all the scientists who are doing it. These are the actual observers.
Yes, exactly. And it'll vary from people who will set up the instrument in their backyard, if they're lucky enough to live right on the center line, to people driving to another state. Say got a lot of interest from people in the Northeast, driving to Kentucky or Illinois to set up the telescopes there. So yeah, it's going to be a very exciting project, and I'm looking forward to participating. If I look through these pictures, a lot of these are my colleagues and became really leaders in solar physics in the 1980s and 90s. And so that's another image to keep in our mind, is that hopefully the people who are involved in the CATE project will become leaders in the citizen science experiment into the future and drive the science. I mean, I just have a few ideas about eclipses and variable stars and comets, but I'm sure when you get 100 smart people in the room and give them a telescope, there'll be a lot more ideas coming out of this, things that we can't think about now. So hopefully it'll take off in exciting directions.
Well, and there are projects like that that engage usually really well-trained amateur astronomers and so on. This one is different in that it's something that anyone can do with a small amount of training, preferably familiar with telescopes. But even at that, this is something anybody could really learn, given a little bit of time. So here's the big question. I don't remember if you gave the answer to this. Somebody wants to get involved in this. What do they do?
Well, we have a Google website, and of course I haven't given it to you, have I? But yeah, we have a little web page that describes the current part of the projects. We update that and show images from Fred's Eclipse expedition. But the main thing is to contact probably me by email if that's a useful thing to do. So my email is simply mpenn@nso.edu, and we have now a set of volunteers who are coordinating the states along the eclipse path. The eclipse will cross 8 states, and one way to break it down is to have people in the states now sort of coordinate who will be at what sites and how they will be trained and when the equipment is delivered to them. So that's sort of the hierarchy that is going to happen in this project. We're hoping to have the telescopes delivered in the early part of 2017, and we'll have some practice sessions on the moon and 1 or 2 on the sun before the actual eclipse day, so that as a team we can work out the kinks and find out, make sure everything's on track for a good experience on eclipse day. But sending me an email, mpenn@nso.edu, is a way to start. And I'll probably forward you to the state coordinator for your region. Or if you're traveling to a particular spot, I'll forward you to that state coordinator as well.
And we can add your email address on the website into comments on YouTube, where this will be archived and people will be able to see the program there as well. One other question: what about people who have their own gear and they just say, "Well, I can do this. I mean, I've done this kind of thing before." These are trained amateur astronomers, and they're going to be able to take good images. Can they use their own gear to do it?
Yes, well, that's a fascinating question, and I have to say that we're very interested in collaborating with people like that. But that's a second-order event. Having 100 telescopes spread out that all have the same focal length and the same image scale is still going to be difficult enough, because on every image we're going to have to do an XY shift and then a rotation to align them. Now, with a different telescope and a different camera, we'll also have to magnify or demagnify those images. So at least in the first cut of the data, we're going to just focus on the people who have the same image scale and the same types of telescopes. Now, of course, I think the vendors will be happy to sell people these types of telescopes if they're interested, as well as providing them to the project. But I would say that for later studies where we can really combine data that's taken at a different image scale, it's going to take a little bit more work, but we're very excited about that option. People, as I said, people are taking images of the sun that rival things that we can do at the National Solar Observatory.
Right.
So there's absolutely no reason to preclude those people from being involved. We're excited to have them on board too.
Well, what about other? This would be tertiary perhaps, but there are a lot of great H-alpha imagers, and I just returned from a meeting down in Brazil, and Pedro Rey from Portugal and Stephen Ramsden from Atlanta, where the eclipse is going, I think, almost through his backyard. These guys really know how to take fantastic images that rival many of the professional places. Are you going to have a use for that sort of thing if the H-alpha imagers decide they want to line up along? H-alpha shows the chromosphere and a little bit of the transition into the corona, but not the corona itself. So.
Right, and so the dynamics of that interface become exciting, and I've spoken with people already who may want to have a few H-alpha telescopes. You can imagine looking at the limb with an H-alpha telescope. You can do that during the partial phases of the eclipse, and so you may only need 2 or 3 to provide a continuous movie of the dynamics at the limb. And this leads into possible ideas for 2024, and some things that my colleagues are doing now. I mean, the corona, as I said, has infrared emission lines, but it also has visible emission lines in green and red and other colors. And so right now the idea for the Citizen CATE project is to just use white light to look at all wavelengths from about 500 to 700 nanometers, wherever the camera is sensitive. But branching off from that and using specific wavelengths like H-alpha to capture the cold plasma, or the green line or red coronal lines, to provide us with very important information about other temperatures in the corona. And so, if people are excited about doing that, then yeah, that would be another way to combine different types of temperature measurements. And for 2024, perhaps we can go that direction too.
Yeah, well, it seems to me that you have your hands full with one telescope and one camera without worrying about differences in spectral response or optical characteristics, and getting into narrow band imaging and everything else, just coordinating this effort. This is really kind of huge, and as we all know, Murphy's Law, the occurrence of Murphy's Law is at a maximum during solar eclipses. Things just go wrong because it's so exciting, and you have 30 seconds, you have 4 minutes, whatever it is, it's never enough time, and your plans are too much. I don't even take pictures. One time I got a new prescription in my glasses before I went to a solar eclipse, and I forgot to put them on. So you don't even need to be taking pictures to have something go wrong.
Oh yeah.
Yeah.
And like I said, we're trying to minimize the activities that people have to do. Right now, it's just a matter of taking the filter off and then putting it back on so we don't melt the camera after the eclipse. And yeah, people will forget to do that, and that's fine. I mean, I've made mistakes as well during eclipses. That'll happen. The eclipse is the ultimate deadline. I mean, there's nothing that you can do. You know that the sun is going to go away for 2.5 minutes at exactly 12:39:40, and if you're not ready, you can't stop the moon. It's going to happen. So there will be equipment breakdown and problems, and so hopefully we'll have enough sites and enough observers along the way to cover those gaps.
Well, I have a feeling if the word gets out here wide enough, and I'd be glad to use our resources to help that happen, you may be inundated. You may not be able to supply everybody with what you need, and you can't beat the weather, but at least you can have people at enough locations. So any place that's clear, you'll get it. So let's hope that works out.
Exactly. I think it's going to be an exciting time, and like you said, it's not that far away. We're working really hard now to get the details in line and make sure everything's working in August of 2017.
Mm-hmm. Well, Matt, this is fascinating. I'm glad to learn more about this project as well, because this is really fantastic, and I'm usually too busy, putting programs together to actually ever participate in anything, and I don't like to do things during eclipses. But this will be an exception. I mean, this would be just a real honor to be a part of. So I hope a lot of people feel the same way.
Yeah, I'm writing your name down, Mike.
Okay. There you go. I want
Thank
that
you.
telescope there. There you go. So anyway, well, thanks for coming on to show us about this and some of the background behind it and the science that people can take part in. Being one of the observers itself, this is just a really exciting opportunity, in addition to the ultimate experience of a total solar eclipse. So I hope the word gets out and you get plenty of people to participate. I think it's going to be great.
All right. Thank you very much.
Well, thanks for joining us, and thank you to all of you who were watching as well. This program will still be available on YouTube on the Astronomers Without Borders channel, so you can still refer people to it who want to learn something about the CATE experiment for the 2017 total solar eclipse across the United States of America. It's going to be a great event, and this makes it even a little bit greater. So thanks for watching, and we'll see you in the next program, which will be tomorrow. Now, this is happening on Monday the 13th, 2015. Tomorrow we will have John Varsic and Claude Plymate from Big Bear Solar Observatory, the other biggest solar telescope in the world. And they'll be at the telescope and show us around and show us what's going on. So be sure and join us for that. And then the radio facility actually looking at the sun in the Owens Valley of central eastern California. on Wednesday. So our week of SunDays continues. And thanks to Matt, and thank you for joining us, and hope to see you in the other program.